So we'll be continuing from our previous lecture on collision theory. So we were seeing the reaction in which A and B were reacting to form C plus D. So from here we can write that minus dA by dt would be equals to K times A and B. Okay, and we can write that as we already know that n star would be equals to n upon v. So just writing here n small a star or n capital A star, anything you can write. This is the number of molecules of A per unit volume. Okay, so this is, let me first write it. Okay, so first let me erase it. So let me write it from here itself. That let's say Na star is the number of molecules of A per unit volume. And Nb star is number of molecules of B per unit volume. Okay, and how will be getting the concentration of A? Concentration of A would be Na star divided by Avogadro number. So Na star upon Avogadro number would give us number of moles per unit volume. Okay, so we can just write here that minus 1 upon Na d of Na star divided by dt would be equals to K times, what would be the concentration of A? Concentration of A would be again Na star divided by Avogadro number. This is Na rather. In the subscript, so multiplied with Nb star divided by Avogadro number. Okay, so we can write N and N get cancelled. So we can write d of Na star divided by dt would be equals to K times Na star times Nb star divided by Nb, rather Na. Nb doesn't mean anything here. Na, yes. Okay, now we know that U average would be equals to under root of 8 RT upon M. We have seen this in our chapter of, rather in our previous set of video lectures on physical chemistry, specifically in the chapter of KTG or kinetic theory of gases. So we can write that, and we can write that we've also seen that rate of disappearance of molecules per unit volume per unit time, rather rate is per unit time only. So the rate of disappearance of volume molecules per unit volume would be equals to ZAB multiplied with probability of collisions e to the power minus EA upon RT. Okay, so Z is the collision frequency and ZAB would be equals to, as seen in the KTG, would be equals to pi distance of centers of molecules A and B squared multiplied with U average multiplied with Na star into Nb star. Okay, where D is the distance between two colliding molecules. This is dA of DAB. Okay, which can also be written as collision diameter. Okay, so just substituting the value of ZAB in the above equation, we will be getting rate of disappearance of molecules of A per unit volume would be equals to pi DAB square times U average times Na star Nb star times probability of collision multiplied with e to the power minus ea upon rt. And we also know that minus d n a star upon dt from the first equation. Here we can write that it is k n a star n b star divided by Avogadro number. This is k n a star n b star divided by Avogadro number. Just equate these two values, so we will be getting k times n a star n b star divided by Avogadro number would be equals to pi dab star dab square u average n a star n b star p e to the power minus e upon rt. So n a star n b star get cancelled out, so we'll be left with k would be equals to pi dab square times u average is 8 rt upon pi m multiplied with Avogadro number into probability times e to the power minus ea upon rt. So this is in terms with k equals to a e to the power minus ea upon rt, which is the RNS equation. So a in this case can be compared directly and can be said that a would be equals to pi dab square root of 8 rt upon pi m multiplied with na times p. So in this case we can write that a is directly proportional to root of t. Okay, next let us see the activated complex or transition state theory. Okay, so this says that a macromolecule is formed by reactant molecules, or rather when a macromolecule is formed by reactant molecules, the resulting molecule is known to be a activated complex, and the activated complex is unstable due to high vibrational energy. Hence the bond rearrangements take place very fast in the transition state, and when the activated complex get converted into intermediate product or products, its vibrational energy converts into translational energy or kinetic energy. So some points here on the activated complex, that macromolecule formed by reactant molecules is called activated complex. Next, that activated complex is unstable due to high vibrational energy. Then bond rearrangements takes place very fast in transition state. Very fast in transition state, and when activated complex gets converted into intermediate product or products, its vibrational energy changes or converts into translational energy. When activated complex gets converted into intermediate product or products, its vibration energy converts into translation energy. Okay, which is the kinetic energy. So with this we come to the end of this lecture and to the end of this chapter, which was chemical kinetics. From the next lecture we'll be taking on a new chapter, which is radioactivity. So till then, good luck and goodbye.